So what I thought we would do today is just very briefly talk about some of the stuff we've done this semester as a way to just recap all the stuff we've done and lead into the different presentations, and then just use the rest of the time. The vote was 4-0. This was the greatest voting we've had all semester in terms of just doing some more practice problems. So I'm not sure how much I'm going to write on the board. I'm a little bit under the weather, but all right. What was the theme of this class? The theme of this class, operations research, is to try to do things efficiently. And for a lot of things, you don't necessarily have to use that high or that advanced mathematics. To make some real differences, just basic stuff that's freely available, simple code, is already enough. And it's amazing how many people do not know how to do things like this. And so in fact, the Math Blast team, where's the Math Blast team? So I've already been publicly commended about the job you've been doing and what a difference you've made for Math Blast this year. In fact, what we probably should have done is we should have had a Math Blast topic of how you got assigned to your Math Blast topic. To just tell the students just how this problem was able to be solved so quickly and so efficiently. So this is a first class in the subject. There is a real tension in the first class as to how deep do you want to go. And my feeling in a class like this is it's often good to just see a little bit what's out there, to be aware of the issues. And then if this is something you're interested in, you now have a starting point to investigate further. So we've seen some of the main techniques in operations research. Now, computer science, for those of you who are taking classes like that, you've seen a lot of these algorithms before, and there's a lot of detail in terms of how you analyze how long these algorithms talk. One of the topics that's going to be presented will be on estimating the runtime of the simplex algorithm. Most of the time, the simplex algorithm runs very efficiently. There are a couple of rare times when it can actually run in exponential time. I'm not sure if it's a theorem that if you tweak it, that there's always a finite amount of tweaks you can find that's constructible. We'll find out next week on Monday that you can get it to run very fast. This is somewhat similar to something we saw when we were looking at the simplex method. We saw that we assumed certain things about the input matrix B. One of the things we have not done in this course is investigate too much the sensitivity of the runtime to initial conditions. This actually connects with something we did on the very first day of class. So I know some of you enjoyed the little fractal movie of Sierpinski's triangle looking at the binomial coefficients modulo 2, and you're seeing the pattern that emerges. There's a lot of wonderful stuff with fractals, where if you change the initial conditions ever so slightly, you now get wildly different behavior in terms of what the system evolves to. In the real world, there is a limit to how well we can observe things. We're not going to have 20 digits of accuracy in our measurements. And so we actually have things fundamentally on a discrete scale. Some of these things are so discrete that it might as well be continuous. Walmart. Is Walmart continuous or discrete? Discrete. When you look at the revenue of Walmart, and you talk about a penny, it's so many magnitudes different that you might as well assume that a lot of these quantities for Walmart are continuous. But on a fundamental scale, it is discrete. If I give you a matrix, if the matrix is singular, you cannot invert it. If I tweak it just a little bit, the matrix is now invertible, and you can get a unique solution. Okay? That's a very small change. So you can ask, how sensitive are things? As your computer is doing round-off errors, how much do these matter? As you go forward in the field, these are extremely important things to look at. So the main thrust, at least of the first half of the course, was on linear programming. And we'll do a bunch of examples on linear programming very, very soon. The idea of linear programming is there's a huge variety of problems that can be put into a common format, and then we can use the same type of machinery to solve them. If you become an expert, if you really work in the subject, there are different techniques that are better suited for one type of problems than another. We have not really spent much time analyzing what is the cost of adding these constraints. How much worse is it to do it this way or this way? An outstanding project, and we talked a little bit about this the last time we met, was looking at the Sudokus, or the Spriner's lemma. If we label the vertices of a triangle 0, 1, 2, or if we label them 1, 10, and 100, is there any difference really between the two cases? No. For Sudoku, if we do the numbers 1 through 9, or 1, 10, I think 10 to the 8th, is there any difference between the two? No. If you've taken group theory, you do some kind of isomorphism, you do some kind of mapping and just flip, 1 to 0, 10 to 1, 100 to 2. But in terms of writing down constraints, we saw that there is a huge advantage to using this approach. We were able to then say, what does it mean for all the vertices to be distinct? It means the sum of the entries is 111. And we don't have to worry about, well, which is the vertex that's 0, which is the vertex that's 1, which is the vertex that's 2. There are 3 factorial ways to assign the different labels. And this is, to me, one of the biggest differences between applied mathematics and pure mathematics. When you're actually coming down and doing things, these things make an enormous amount of difference in terms of the runtime and the efficiency. As a great exercise, it would be interesting to see how much longer does it take to solve some of the problems if you don't do something like this, if you actually encode all the different constraints. The other thing which we're not getting into in this class is different computer systems work better with different types of input, different types of data. MATLAB, my brother works for the company that makes MATLAB, they love vectorized inputs. And it's really optimized to work well in stuff like that. Depending on your problem, depending on the system, different types of computations actually turn out to be easier than others. So one of the things we saw time and time again is we can convert problems to linear programming problems that can then be solved. And then the big thing was, what kind of constraints can we handle? And this is where we spend a lot of time talking about how we can linearize things. This does not mean we're making it a linear function. It would be wonderful if we could make things a linear function. We can't do that, but we can handle it within the confines of linear programming. But there's a huge cost. What's the main cost whenever we make linear these different constraints? What do we have to introduce? Discretized parameters. We have to introduce these binary or integer valued parameters. And this is the real problem. If we do linear programming with real inputs, it's fast. We have good algorithms to solve this. If we do linear programming with discretized, with discrete, with integer valued inputs, we no longer have algorithms that run quickly. But we can often get very close to the right answer without spending too much time. And this is one of the main things that is very different than a theoretical math class. In a theoretical math class, if we're trying to solve a cubic, we want the roots. But then as you go higher, well, maybe I don't need the roots exactly. Maybe I just need something that's close. Well, it depends on the problem. For some things, we need to know exactly what the roots are. We may care about the algebraic structure. And if I chop off at the 100th decimal place, it's going to make a huge difference whether or not my number is rational or irrational. Can computers work with irrational numbers? Okay, so why not? I see somebody shaking their head no. Yeah, all a computer does is it works with zeros and ones. Fundamentally, that's what it does. There's some joke emails about somebody coding in unary, but computers work in 0 and 1. You can work in other bases as well, but fundamentally, you've got some fixed integer base, and you're just playing a finite number of games with integers. You can have really good approximations, and there's a huge theory in mathematics devoted to how well can you approximate general numbers by rational numbers. But at the end of the day, the computer is just working with integers. And so in terms of your linear programming, in terms of trying to get your optimal solution, what you have to remember is we often don't know the correct values that's going into these programs. And so when we're trying to get the exact answer, you're trying to get the exact answer, but with non-exact inputs. And so how upset do you want to be that you can't find the optimal answer? I mean, it still seems that you want to get as close as you can. But in terms of how big of a deal it is, well, do we have any way to quantify how close we can get? Do you have any way to know at least how close we are? Yes, what is it? This is the last day for class participation. How do we tell how close we are? We had a great method in the beginning of the semester to say how close our answer was to optimal. We looked at the dual problem. So when you develop the theory even more, the dual becomes incredibly important. There's a lot more stuff in our book about the dual problem. In the first course, there's a limit to how much we can get through. But if you think about it, this is essentially almost the best thing you could ask for. If you can't find the optimal answer, can you at least say how close you are? And after a while, you can see, I'm so close, I don't really care about all of this. Yes, I'd love to make an extra $50,000. But if my scale is on the order of billions of dollars, $50,000 is insignificant. Okay? So you really want to get a sense of what the correct scale is. And so the dual problem, when you're trying to solve like the traveling salesman problem is very tough. To get close to the optimal solution is not that bad, and we can even quantify how close things are. So some of these things in passing, it's not easy at first to realize how important they are. If you look at some of the original papers in linear programming, they actually have some very cute remarks about how this is completely impractical because it would require you to do thousands of calculations an hour. And it's going to be impossible to be doing anything of that order of magnitude. Well, now of course, thousands of calculations in a tenth of a second is no issue at all. And so, progress happens. In terms of, if we get quantum computers, I have no idea what consequences that would have. So that's, the first main theme of the course. And we talked a lot about different algorithms. We talked a little bit about analyzing the runtimes. There's lots of different metrics you can use: average time, best time, worst time, median time, mode time, lots of different things. Certain computer science classes really get into analysis like this. We haven't talked too much about it, but just trying to give you a sense of what's out there. There's also randomized algorithms. And so frequently what you might do is you might have a couple of different algorithms. Let me give you an example. If you haven't seen this concept before, so we have method 1 and we have method 2. And most of the time, method 1 is the best way to go. Average runtime is 1 second. Occasionally, occasionally it takes a lot of time to run. And method 2 is always 1,000 seconds. Okay? Which algorithm do you want to use? 1. What happens if you take 1 and it's taking a while to spit out an answer? 2. So what you would do is you would use 1, and then if it's taking too long for 1 to work, stop and switch to 2. Right? Now, it might be the case that if you had just waited an infinitesimal bit longer, 1 would have terminated. And sometimes you don't know how close you are to terminating. And so you may have switched to 2 just a little bit too long. So it then becomes an interesting question: how long do you hold with 1 before you give up and go to 2? Any of you who have ever been waiting in a slow line, you've faced this problem. At what point do you give up? We have this mentality: I've stuck it out this long. I'm gonna wait. And just to say it's a lost cause, let me just cut my losses and move to something else. So one of the ways that we go in the future is we actually have a bunch of different algorithms that we can toggle between. And it becomes a very interesting question as to, given a collection of algorithms, what is the best way to piece them together to attack a problem? So I'm just trying to give you a sense of where everything goes. The next major theme we talked about was fixed point theorems. Who are the econ people in the class? Okay, so hopefully you've done some of these fixed point theorems, some of the Nash equilibria in your classes. Yes or no? Okay, did you ever prove why these fixed point theorems? No, okay, not even close. No, right. So Moses came down from Mount Sinai, and in addition to laws as to how we should live and talk and behave with each other, he also gave us some fixed point theorems. And we can just use those. So one of the reasons I want to spend some time going through the proof of the fixed point theorems is these fixed point theorems are essential for so many different things. One of the main reasons is because if you want to solve f of x equals x, just look at the function g of x is, what was it, f of x minus x? And trying to find where the function g is equal to 0 is the same as trying to find x such that f of x equals x. This is a fundamental idea in mathematics, is to look at equivalent problems. The idea of finding a fixed point, it's really no different than trying to solve a related problem. It's which is a good interchange to do, which is a good thing to look at. So we did one type of fixed point theorem. We did the Brouwer fixed point theorem. This is one of the big guns in modern arsenals. The book talks about other fixed point theorems that lead to Nash equilibria. You're now at the point where you can learn and use these. So the real question becomes, as a practitioner, how much of this do you need to know? When you're doing economics, you can just assert that a solution exists. And frequently, you can even say, well, look, I have a contraction map. I have some way to find, I don't necessarily understand the proof. Well, hopefully you do here. But I have a constructive way to find the solution. So there are a lot of times when you do not need to know the nuts and the bolts. One of the reasons I'm a theoretical mathematician is I believe there is an advantage from knowing the nuts and the bolts and knowing how an algorithm works. And if you know how something works, you have a better understanding of its limitations and a better chance of using it well. And so this is one of the reasons why I want you to get a sense of how these different fixed point theorems work, where they can be used for. We can use them for solving differential equations and proving solutions exist and are unique. We can use them for finding fixed points. And that allows us to solve equations like this. We didn't cover the economic stuff. There's only so much we can get into, but you can now read Nash's thesis. It's 20 pages. It's worth reading. And this is 20 pages, spaced out, typewriter font. It's not going to be that bad. And this is one of the most influential theses written of all time. One of the best advices people often given is go back and read the masters. Read the papers that really made a difference. Okay, and then the last thing we talked a little bit about was just some of the algorithms. We talked about Gale-Shapley, and just there's a whole slew of things like this that are out there. So when you get a problem, one of the things I want you thinking about, post this class, post Williams, is what have you seen that's similar? You do not need to reinvent the wheel. And in fact, there's lots of, not just the wheels, but there's a lot of cousins of the wheels that are out there. And the more you see, the more connections you can make. You say, hey, this looks vaguely like blah. And that's one of the reasons why you probably don't sell books if you have books, or you have good sets of notes. You want to try to say, where have I seen something like this before? What can I go to that has done this? Any physics students here? Not many. Okay, in physics, you study gravity. And the gravitational force is proportional to 1 over the radius squared, where the radius is between them. Any other forces like that in physics? Electricity. So really, you can almost do a search and replace at times in terms of a lot of the equations that arise in electricity have occurred in gravity. Now, there are some fundamental differences. We don't yet know of anything that's negative matter in terms of a negative mass charge, but we do have positive and negative charges in electricity. So there are differences between the two subjects, but there's a lot of commonalities, and you can quickly apply things you've learned in one area to another. So if you're doing a scheduling problem, odds are somebody has looked at what you're doing, and odds are somebody has seen the issues you've had. The question is, can you find what it is? The other thing is, if your problem is of modest size, you don't have to be that efficient, because computers are getting to be so good now. When I was an undergraduate about 20 years ago, I remember I had to deal with the people in the library. They let me come in on a Friday, and right before the library closed, start running my code on their computers. And my boss was fine as long as by Monday morning, I would come in and give him back his desktop. He was fine with it doing number theory calculations. And I needed to do this, because I needed to get lots of data on primes. You can now get this data so quickly and so rapidly, it doesn't matter anymore. All right, so this just gives a brief summary of what we've done, the different connections between them, the common themes, trying to be able to use good mathematics to solve things efficiently. One of the things we haven't touched upon too much, we did a little bit when we looked at the movie paper, was how do you get the input for stuff like this? This is where statistics really comes into play, where you somehow observe things in the real world and you use this to infer what should be the parameters of your model. Did I tell you the story about my father and the equation with 46 variables? He was getting his MBA, and he had one of these highfalutin academic professors who gave them an equation with 46 variables to describe what your company should do in all configurations. And my father looks at the equation and says, I don't even know the values of these variables for my own company, let alone for my competitors. We don't have this information. And she just couldn't understand why he was complaining, because this equation tells you exactly what you should do. But it was completely useless because you did not have knowledge of the parameters well enough to understand what was going on. So in the movie paper, we talk a little bit about how you try to estimate the demand. If you can't estimate the demand well, you're in trouble. But then there are other situations where you could have wildly different situations and you don't know what's going to go on. And one or two of you have emailed me about this. One of my students, Faraz, did this a couple of years ago, where you now have probabilistic programming, where you look at a bunch of different scenarios, and you have, I want to optimize a bunch of things simultaneously, maybe minimize my exposure. And then this is very similar to the multi-objective programming we have. When you have lots of different opportunities, what do you care most about? And so you can handle linear programming problems, this is now called stochastic, where the parameters for the problem are variable. What this could be is maybe the cost of food is not constant. And if you're trying to figure out your diet over the year, things may be changing. This is why a lot of big utility companies, they often buy ahead of time certain things, certain resources to limit their exposure. And again, it does possibly decrease their profit, but it does also protect them from what could happen. So for the last bits of the class, I thought we would go through some of the practice problems. If anybody wants to walk out, if you're comfortable with how you're doing on linear programming, I'm not going to be insulted. If anybody has any particular problem that they'd like to do from either the list I sent you or from anything else, let me know. Make sure you grab old homeworks and old exams afterwards. Any problems people liked from the list? Which one? Okay, Battleship. All right, so the way Battleship works, we have some grid like this, and maybe you've got a couple of ships, and I think it says you're not even allowed to have them touching diagonally. So I can't put another ship here touching here. I forget what the constraints are, but we'll just put something down now just so we have something. And the way it works is you're told how many elements you have in each row, how many elements you have in each column. So here I would have 3, 1, 4, 0, 5, 0. Here I would have 3, 1, 3, 3, 3. And you want to try to figure out where the ships are based on this information. One of the most important things is to understand what is the problem you are trying to solve. Just because somebody tells you to solve a problem does not mean that is the problem you are trying to solve. What is our goal here? I'm sorry?
To construct a battleship, or using those constraints.
So let's say however many dots there are, that's how many shots I have. And I can fire my guns that many times. Each gun destroys one part of a ship. What's my goal? To destroy the enemy fleet, right? To protect Williams from the horde coming from Amherst, right? To destroy the fleet. Do I care if this is the cruiser or the submarine? No. So in terms of where the ships are, do I care where the ships are? Not quite. I don't care where the ships are. What do I care? It's very close to that. Not quite. In some sense, that's a good way to say it. I care about where the ships aren't. I care about which squares are occupied. So there's not always going to be a unique solution. Imagine I have a ship of 2 units and a ship of 4 units and a ship of 3 units and a ship of 3 units. Not drawn to scale, not even closely drawn to scale. Okay? Can you think of another configuration that would be indistinguishable from this? Flip them, right? So depending on what my configuration is, I may not have a unique assignment of ships to the board. So if the problem is asking you, can you uniquely determine where the ships are, the answer is going to be not always. But just because somebody tells you to do something, should you do it?
Depends who the person
is, right? There are certain people that if they tell you to do something, yes, that's the correct answer. There are other people who you want to politely say, oh, okay, but do you want me to do that, or is really what you want? And you have to figure out diplomatic ways to say this. The problem here is not to find out where the ships are. The problem is to find out which squares are occupied by ships. And again, this slight change in perspective is very valuable. So now we want to try to figure out, how do we tell if a square is occupied? What do you think our variable should be? So, for me, step one is always to figure out what are my variables. And then I try to put in my constraints and my objective function.
Well, I mean, we have an I by j grid, and maybe we could just say xij is equal square.
So xij is going to be what?
We can set equal to 1 if it's a square that has a ship.
Okay.
0 otherwise.
So this is one way to do the problem, is we could set it up so that it's just occupied or not occupied. And then at the end of the day, we have to figure out which squares are occupied. Now, what I drew a moment ago with the 4, 2, and the 3 and the 3, that might not actually be permissible according to this rules of Battleship. Did the instructions say you can't have ships touching? So when you put that constraint in, there's now a separation between ships. Do you think that's going to help us or hurt us in terms of the programming?
It always hurts when you have to add another constraint. Or I may be wrong. I should say always.
Wouldn't that help us? Because it just sort of, once you know one of them, you have more of a better idea of where the other ones are.
Right, because once you know you've got something here, as soon as you hit a blank, you know, okay, my ship has to be continuing in the other direction. When you're playing Battleship, it's been a while since I've played Battleship. When somebody says hit, do they then say hit my sub, hit my destroyer? Or do they just say hit? It's only hit and sunk, right? So if you have, in Battleship, if you have a 3 and a 4 over here, and you first hit here and then hit here, you've hit 2 different ships. But you don't know that yet. This is not designed so I can justify using my research funds to buy Battleship. That's just a nice bonus. Okay? So if people want a Battleship game, let me know. But in something like this, you don't have extra information. You don't know where you are in the supership. If things are separated by at least 1 unit, however, much, much nicer. You know, as soon as you hit a blank. So I would actually say that the more general problem where you allow ships to touch is much, much harder. So here, I might want to do something more than just xij. What might I do for variables? See, I might view this almost more like a movie. For each square, I have a choice. This is my screen. Screen 1, screen 2, screen 3, screen 4, screen 5, screen 6. On each screen, I can choose, do I want to start showing a ship? And if so, in which direction do I want to start showing the ship? I will always assume that for each square, I either show a ship going to the right or a ship going down. Because every ship has to have a point that's furthest to the north. So I can have x, I, j, t, s, r, and maybe x. So this is going to be if at square ij, we start ships S going in direction D. And D is either going to be right or left. So ij range over grid, S range over ships, and D equals 1 for right and 2 for down. And so now I'm choosing where do I start my different ships. Yes?
If you have the bottommost ship or the rightmost ship, how would you differentiate between two that would be 0 for each of those?
I'm sorry, the bottommost?
What?
So for something like this, each ship is going to have a unique point in the upper left.
Okay.
Now what we need to do is now we need to just go through all the different constraints. Yes?
Does it matter that under
Well, we know that there has to be a separation between ships. So what we can know is that if we start a ship at I and j, we know how long the ship is. We know that all these other squares around it can't be used. So now we need to start putting in all the different constraints. So it's time to go. If anybody wants to stay, please stay. If not, I'll record this for another few minutes. So if you're not able to stay now, it'll be posted later. We know that if we start a ship here going to the right, then all the squares underneath it and around it are inaccessible for starting points. So in terms of our constraints, there's a lot of ways to do that. You could decide if you want to have secondary variables to, is the square occupied? And if I start a ship here, then I've immediately set a bunch of squares to be occupied and a bunch of other squares to be unoccupied. That's a perfectly fine way to do this problem. But again, for stuff like this, it's always, is this similar to anything you've seen? I actually think that this is very similar to the movie problem. And these are my screens. We don't know that many things. Mathematicians are lazy. You always try to reduce things to something you've already seen. Now that you've got this hint of trying to do this as like a movie scheduling problem, now you want to start putting in your other constraints. What are your constraints? Each type of ship has to occur someplace. So if I sum over all I and j, and I sum over all d of xi, j, s, d, that has to equal 1 for all s. Each ship is placed in exactly one place. See how easy it is to put these constraints in. Now at the end of the day, based on where my ships are, if this is going down, then I know that that's going to be contributing to the column sum, the length of the ship. If it's going down, it contributes to the row sum exactly 1. And so now you can put in all these different constraints. So this is a really good exercise to prepare for the exam. If you can do a problem like this, you're fine. All right, it's been a great semester.